Hello, my name is Varun Chandrasekharan. Together with Brian Tang, we'll be presenting our work titled Face Off, Adversarial Face Obfuscation. This is joint work with Shuhan Gao, Kasim Fawaz, Somesh Jha, and Suman Banerjee from the University of Wisconsin. Facial recognition is the technology where machines can identify faces from video streams or images. This has many uses, such as in airports, to make the check-in and security procedures more seamless, finding missing pets, or even improving filters and backgrounds in web-based communication applications. With the increasing use of facial recognition by law enforcement and government entities, we're in a scenario where users have few options to preserve their visual privacy on the internet. Some companies, like Clearview AI, have even scraped private and public profiles from Facebook for faces. Data leaks are becoming more common, leading to more fear in user minds. So how does a concerned user protect their privacy, their facial information, while using social media and photo storage sites? There are several options, but each have their own pros and cons. One can easily blur or pixelate their face, and this provides strong privacy guarantees, but it deprives the user of any utility benefit obtained by uploading images on social media platforms. The work of Sharif explores using physical wearables that fool facial recognition models. Using insight from evasion, they propose an approach that enables a recognition model to mislabel a user. While these are more usable than the previous solution, they still require the user to modify their image to include wearables. Additionally, their black box algorithm requires providing their optimization procedure the original facial input whose privacy they wish to preserve. This leaks information about the input. Shan and his colleagues used data poisoning to corrupt the training of facial recognition models. However, this approach assumes the recognition models are trained on public data and will include the poison face image in the training set. At a high level, our solution, FaceOff, digitally adds strategically generated noise to input faces. This results in online facial recognition systems being unable to correctly identify the face. Better still, it does this without requiring access to the online facial recognition model. This process is as follows. First, a user chooses a photo with a face to mask. Then, FaceOff generates strategic perturbations to the face and reinserts it into the original photo. Finally, the user can safely upload the photo to any social media site or cloud provider, and the face will be tagged as a different identity. Note that FaceOff does this without negatively impacting the facial detector, permitting downstream applications. To better understand how FaceOff works, let's begin with a primer on facial recognition. First, a service identifies the region of the face. Then, this region is cropped and resized as needed. The cropped face is fed through a deep neural network for processing, and the DNN returns an n-dimensional vector embedding as an output. This embedding can be used in a variety of ways, such as for clustering, matching faces, or classification. More concretely, facial recognition is based on metric learning. Metric embedding networks are very similar to deep neural networks that are deployed for classification, but with some minor differences. Instead of cross-entropy loss, contrastive loss functions such as the triplet loss is used. Here, a learner first samples random sets of 3 faces to train on. One is an anchor. The next is a positive sample, which matches the identity of the anchor. And the third is a negative sample, which has a different identity. The goal of the loss function is to minimize the distance in the embedding space between the anchor and the positive sample, and to maximize the distance in the embedding space between the anchor and the negative sample. After training, the embedding space should look something like this, where samples of Morgan Freeman are close to each other, and the same for Taylor Swift. When a new unseen face is introduced during inference time, the network measures the distance in the embedding space to different cluster centroids and determine which identity it belongs to. To generate masks, we utilize insight from previous techniques for evasion, which were primarily developed in the classification setting. A very common example all of you must have seen is this panda. The classification network predicts the label of this image correctly. To ensure misclassification, human imperceptible noise is added to the input. This noise is generated by these optimization functions, which minimize its perceptibility while ensuring that it induces a misclassification. Some commonly used attacks are the fast gradient sign method, the Carlini-Wagner method, and projected gradient descent. Finally, this noisy panda is misclassified by the network as a gibbon instead of a panda. For reference, this is a gibbon. In our work, we addressed the following two challenges. To the best of our knowledge, there were no known attacks against metric learning systems. We do not have access to the internals of the models deployed on the internet. In particular, we operate in the black box setting without ever revealing the actual input whose privacy we wish to preserve.
We now describe how we address challenge 1. Observe that in normal scenarios, the embedding for a face is going to be closer to that of its source identity. We create masks for faces such that the embedding of the masked face is further from the source identity and closer to a target identity. In the embedding space, this can be visualized as follows. The embedding is close to its source, and our attack moves the masked embedding closer to the target. Here's a simple formulation of our attack. L denotes the new loss function we formalize, which tries to ensure that the masked face is closer to the target than the source. Delta denotes the generated perturbation. Kappa is the margin, and this can be thought of as the separation between the distance of the source centroid and the distance to the target centroid. Mu is some distance metric, which is used to measure the perceptibility of the perturbation. Do read our paper for more details regarding the actual formulation. The previous formulation assumes white box access to the model, which is not the case in our setting. To enable black box attacks, some solutions do exist. We can use expensive techniques like gradient-free optimization to learn gradients, which can further be used for downstream evasion efforts. We can reverse engineer the black box model's parameters using model extraction attacks, or we can generate adversarial examples that transfer from one model to another. Learning gradients through black box techniques is often query inefficient, as demonstrated in prior work. Model extraction is unfortunately computationally expensive for complex models. In addition, models are sometimes updated, requiring continual extraction. So these two approaches are not very practical. Instead, we transfer the masks we generate in the white box scenario over to unknown models. However, transferability itself is not a precise science and is still not yet well understood. To better achieve transferability, we leverage the process of amplification to increase the strength of our attacks. Given a normal image of Matt Damon, we can generate an adversarial perturbation to mask the image. We then amplify the perturbation with a constant alpha, which is greater than 1, to achieve a stronger yet more noticeable masked image. Here you can see how amplification can push adversarial examples across a decision boundary that we do not have access to. This is denoted by the white line in the figure. And as you can see, larger amplification factors results in more transferable attacks. To empirically validate our intuition, we ran an experiment with two FaceNet models trained on different datasets to see how amplification affects transferability success. The trends follow our intuition. Greater amplification improves transferability, which is on the y-axis. In our evaluation, we wanted to understand the following. Do faces masked by face-off transfer to commercial APIs in a black box setting? Can commercial APIs deploy defense mechanisms against face-off, such as adversarial training? And finally, are users willing to upload adversarially perturbed faces to social media, or are they too unsightly? For our surrogate white box models used to generate masked faces, we use FaceNet models trained using different contrastive loss functions and different datasets. We evaluate our masked faces on 3 APIs: Azure Face, AWS Recognition, and Face++. And the faces we evaluate on are from a set of 10 diverse individuals listed here. we discovered that masked faces are misrecognized on commercial APIs. From this study carried out in 2018 on the AWS Recognition Service, notice that the general trend is that increasing amplification causes the perturbation norm to be larger, and as a result, the matching confidence of the service provider decreases below the 50% mark, indicating a successful transferability. We also observed that increasing the margin does not have as prominent an effect as increasing the amplification. Also, amplification is done as a post-processing step and is not on the critical path. We also verified if these same images were misclassified in 2020, 2 years after being generated, and we observed that with larger amplification factors, they still do. We also observed similar trends for Face++ and Azure Face as well. Adversarial training is one of the most robust defenses against evasion in the classification setting. To understand if defending against face-off is possible, we perform a type of adversarial training where half of the training samples are adversarially perturbed. Holding all parameters constant, we train a FaceNet model on 2 different datasets, and we evaluate them on a test set of normal images for 2 types of distance metrics. Observe that the accuracy on the adversarially trained FaceNet model is much lower than that of the naturally trained FaceNet model. This severely hampers usability of such recognition networks. In summary, we find that adversarial training does improve the robustness of the network, but it decreases the matching accuracy significantly. Finally, we wish to know whether users are comfortable with the faces generated by FaceOff, comfortable enough to upload them on social media. So we performed 3 user studies, and for the first 2 studies, we consider portrait images, where the desired subject is at the center of the images, and background images, where the desired subject is at the background of the image. We ask users to rank their comfort of uploading said images. And in the last study, to maintain the ecological validity of our scenario, we ask users to upload and mask their own faces using our face-off web service, and rank whether they'd be comfortable uploading the result to social media. We found that users are generally more comfortable uploading lower amplification images to social media, and they're also more comfortable uploading background images, but not comfortable uploading portrait images of faces. And finally, in our last study, we found privacy-conscious users are also comfortable uploading their own masked faces that were output by our web service. Now let's look at some of the examples of masked faces generated by FaceOff. Looking at the faces of Morgan Freeman and Matt Damon here, the perturbation on Morgan Freeman is centered around the nose, whereas on Matt Damon, it's the entire face. These differences in perturbation styles are a result of varying the amplification factor, the surrogate model used in the attack loop, the source target pair selection, and other factors which we discuss in the paper. So, in conclusion, we've discussed that online and cloud-based face recognition harms user privacy, and there's few options the user can take to preserve their face data. Evasion attacks in the form of adversarial examples allow us to evade face recognition models while maintaining the utility of the masked face. A user can still upload their photo to social media this way, and we found that privacy-conscious users are willing to protect their faces at the expense of minor perturbations and noise. And for more information, please check out our paper or our GitHub or our website, or contact us at one of the emails listed here. Thanks everyone for listening.